we'll use happy blue. Put a happy little chapter 12 here somewhere. There it is. That's better, right? All right, so we have chapter 12, right? And we went through in our lecture, and we have the Maxwell equations, and the lecture slides have a little bit more information on it, right? It's using basically the TDS equations and the Helmholtz and the Gibbs function, and we created these four equations that are very important. That if we do check for our exactness setup, we get these four partials. Okay, so that allows us to relate a partial, let's say with entropy, with one that doesn't even require entropy, that has all measurable quantities, pressure, temperature, and specific volume are all things you could measure for a substance and then relate it back to entropy, right? So we have these four Maxwell relationships that allow us to substitute something in that's not as easy to work with something that is easy to work with, okay? And they all come from these four equations. Each one comes from each one of those equations. And then using specifically one of the Maxwell equations, the third Maxwell equation, and just for a phase change, we derived the Clapeyron equation, okay? Okay, so we went through, derived, and we saw for a phase change process that from that third Maxwell relationship, we simplified and substituted, and we got down to an equation right here. And I think we did either an example in the lecture slides or an example in the examples we did within that chapter on this equation. Okay, so this one you see relates the saturation curve. So at any point, what that saturation curve, so what the temperature and pressure, when it's converting from a saturated liquid to a saturated vapor, the slope at that point, right? So this is the saturation curve, and then here we have the slope, right? That's that partial, right? So that relates us that slope to our HFG, so our latent heat of vaporization, and temperature and specific volume, right? So temperature, specific volume, both of those measurable properties. Same with the saturation curve is another thing that's measurable. Okay, and then we had another version which I don't have in the slide, but it takes this a little further and has the Clapeyron-Clausius equation. Okay, so that now relates it to the saturation temperature and pressure. That if you knew, let's draw this a little different. It helps you if you knew, say, something here to get values here. Okay. And then we had other equations that we went through in I'll talk about that a little bit later, so we still have some more here. We have the Joule-Thomson coefficient, right? So this is during a throttling process. So when H is constant, okay, it sets up that partial H is constant, right? And we're just checking how temperature is going to change as we change pressure, right? So if we change pressure, because we're throttling and restricting the flow, changing pressure, how does temperature change? Okay, so that's what that partial is just describing. In words, that's the math equation, right? And so we see whether temperature is increasing, remaining constant, or decreasing. Okay, and we also set up and created another version of that equation right here. Okay, so that was from the change in enthalpy equation, which you'll see in a second. So it was from the change in enthalpy equation, we derived this one just by setting delta H equals 0, and we came up with this new equation for the partial, okay, or for the partial of the Joule-Thomson coefficient. Okay, so we can here use, properties. So this one up here, if you had R134A or water, right? Because we have all the properties there for that. This one down here would be, say, if you had an equation of state. Of course, if you had properties, you could do the one at the bottom too, but it's, a little more time consuming because everything here is just properties, temperature, specific volume, pressure. So all those things you could also do with properties, but when you have properties in enthalpy, it might be easier just to work with the simpler one, right? But here you have equation of state, right? An equation of state relates pressure, specific volume, and temperature with an equation. Like the ideal gas law is one version of the equation of state, of an equation of state. So we can then utilize that to get that partial in there and simplify our equation to see whether temperatures, when we throttle that fluid, temperature would increase, decrease, or stay the same at the outlet. All right, then we did, so this is the general equations, let's just say, okay, still chapter 12, right? So this is where we started and derives, and there's another slide or two in the lecture, in the chapter 12 slides that had a little bit more with the steps and everything, but we went through and described and derived basically an equation for the change in internal energy as a function of temperature change and pressure change. And it's good for any substance. This works for water, R134A, air, CO2, anything can actually, you can get the change in internal energy for everything within this equation. Okay, so for an incompressible substance, ideal gas, anything will be described by this equation. You can simplify to the versions that you have for an ideal gas from this equation. So it works for any substance, right? So we went through and derived that. So if we had data, everything here is just temperature, pressure, specific volume. So this is all from measurable properties, right? Or if we had an equation of state, we could also use an equation of state and just get that partial and then go through our steps, get what that change in internal energy is. Here's the version where we went through and got for change in enthalpy, right? So this one was our change in internal energy, the general equation. Here's the change in enthalpy. And again, there's more steps in the chapter 12 lecture, but we ended up going through and doing something similar for enthalpy, where we got an equation that's only a function of measurable properties, pressure, specific volume, temperature. Okay, so we have something here where if we have data, we could go through and here, or if we have an equation of state, we can just get our partial, right? Another version for change in enthalpy is just using the definition of enthalpy is just HU plus PV. So delta H would just be delta U plus P, delta V plus V delta P, right? Well, they just, in this version, they just leave it together. Yeah, they don't even separate this. They just say so delta U plus delta PV, right? And this is again measurable. So if you had, say, the equation for delta U from here, and you set up delta U, then pressure and specific volume are also measurable. So you just have to put this part in. On top of that one, you have change in enthalpy. So. All right, what I mentioned here, the Joule-Thomson, came from this change in enthalpy equation, right? If we have a throttling process, we take this equation, we go, okay, throttling process, delta H is 0, right? Enthalpy is being held constant. And now we have dP, dt. If we put those together to create that dt, dP, so move it around, divide it, it becomes a partial because we're keeping enthalpy constant, right? So it only works during that enthalpy constant, right? So we created, from this equation, we basically created this equation. Or I should say, the easier one is from this one, right? So delta H0, and then we're looking for dP, or dt, dP, keeping enthalpy constant. So move these around, right? Divide dt by dP. All right, so that would be a version that we use this equation to get the Joule-Thomson coefficient. We could also use, let's say we use this equation here, right, for internal energy. We could also look at a process if we had a change in internal energy for a isothermal process, right? If it's isothermal, this goes away. So then you would have change in internal energy would just be this for a isothermal process, right? Or if it was a constant volume process, right? And this goes away, specific volume 0, and you're just left with this part. Okay. And you do something similar with this equation for change in enthalpy too. Think about isothermal process or constant pressure process and create a simplified equation there. All right, so now we switch in this review to chapter 13, okay? Chapter 13 just deals with mixtures. How do we get properties for mixtures, right? When we had all our stuff beforehand, it's just one substance that we're looking at. Like it's flowing through a turbine. It was just, you know, air or water or steam or something like that. So just had, you go in the back of the book, you look up the properties for that one substance, and you have it here. Now in chapter 13, we have mixtures, so we have to get our properties. So it's all about getting the properties that then we could use of the mixture for anything from those earlier chapters or later chapters. So if we had a mixture flowing through a turbine, now how do we get that enthalpy, or how do we get that specific heat for if it's an ideal gas, right? So then we can utilize, and how do we get that value so we can utilize those properties of the mixture, right? So the equations, as you hopefully saw during my lecture in the example problems, the example problem for chapter 13, I think simplifies the equations that you see here, because when you look at this slide, you just see summations everywhere, right? So it's just summation, 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 right? So it makes it look more, at least I think, a little bit more difficult than it actually is. And we set up a table, right, to get our properties, and I think that simplifies things a great deal, right? And it really, the main things within the chapter are your conversion, basically from, you have mass over moles. So that's your molar mass, right? So that's the big thing is, if you had moles, you know, you can use molar mass to go to mass. If you have mass, you can use the molar mass to go to moles, because, you know, molar mass is just in SI units, kilograms per kilomole, right? So it allows us to convert from one to the other, okay? And that's what they're kind of doing here for this mixture as you work your way through the mass of the mixture, summation, or you can use the moles times the molar mass, right? And then they simplify mole over the moles of the mixture to get your mole fraction, okay? And they do a similar thing. They start with the same equation, right? It's the same equation they're starting with, but they're going to mess with the moles instead. So keeping the mass here, now for the moles part, they put in the molar mass and just convert mass to moles using the molar mass. Okay. Do the summation, they divide by this, and that's why you see it down here in the denominator. And then the individual mass divided by the molar mass is your mass fraction. Okay. So they've just went from moles to mass or mass to moles. Okay. And the simplified version of that is just, here's your mass fraction, right, with the definition of what that is, the mass of that component divided the mixture mass. If you wanted then to go to get the mass fraction of an individual component from a mole fraction, right, derive it by just putting in the molar mass again for the mixture and the individual component. And you see this is the mole fraction, so that's why it's Y now, and you just have molar mass converting between the two. Mass fractions have to sum up to 1. We talked about Dalton's law and Amagat's law, so that's where we have basically for ideal gases, it's where Dalton's law, where you sum up your pressure of the individual components, you sum them up to be the mixture pressure. So like in the example we did in chapter 14, so even though this is 13 and 14, 15, sorry, chapter 15, when we looked at the exhaust, right, that was coming out of a combustion chamber, and we summed up, we needed to get the pressure of the water vapor, right, and it had a mixture, all those products that were there. And if you think about it, if you sum up all the pressure of all those products, you get the mixture pressure, right, of the exhaust, the total. So we just wanted the pressure of one of the individual components. So that's where we just related, we basically use this version right here, the pressure fraction. Okay. You have the mixture pressure, and you have over that would be the component. So we used water, right? So let's look at it like this. Pressure of the H2O in that example we did in chapter 15 over the pressure of the mixture or the exhaust. Right? And then you can do that same kind of thing with volume also. Okay, sum up the volumes of each of the components, and that equals your mixture volume. So if you want the fraction, it's just your individual component over the total mixture's volume. When it's an ideal gas, because this was talking also about real gases, when it's an ideal gas, in the lecture, we showed that using the ideal gas law, you can take this pressure fraction here, and it actually simplifies to just the mole fraction. Okay, same with the volume, that simplifies to the mole fraction. So that means we can relate this pressure ratio here that you see, okay, or volume to the mole fraction. And that's what we did in chapter, in that chapter 15 problem, we used this and this, right? We had pressure of the water, and the exhaust was the pressure of the exhaust, right? Because the exhaust is a mixture. And then we had the moles of the water over the moles of the exhaust. Okay. As the exhaust again is the mixture, so we just basically summed up all the components of the moles and got the exhaust. And we had an exhaust pressure, 100 kPa. We can get the moles from our chemical balance, right? And we got our water. Okay. All right, properties. Okay, the big thing now, if you have a mixture, is summing up the individual components. So if you want total internal energy of the mixture, you're just summing up the components version. Okay, summing up the components. They're just doing a mass-based one right here, mole-based. Okay, if you want change, okay, it just puts in the delta for each. Okay, so this is with internal energy, with enthalpy, with entropy, right? Where simplify it for enthalpy, if we had a process that's an ideal gas, we could take CV delta T or CP delta T, and then we would just need the CV or CP of the mixture, right? Or we could use enthalpy or internal energy, right? So if we wanted to do that, the other big thing is if your property, right, so this doesn't have the bar over the top. This one does, right? So that's per mole, or per kilomole, right? So if it's per kilomole, you're going to be using the mole fraction of each component times that component's property. If it's per kilogram, you're going to be using the mass fraction, okay, times its specific heat. Okay, so that's the difference of this column versus this column of setups. This is per mole, or sorry, per kilogram, right? This is per kilomole. All right, so then we shifted to chapter 14, okay? And there's some new properties. We have the absolute or specific humidity, okay, which is just the mass of the vapor over the mass of the dry air, okay? And there's a version when you put in the ideal gas law that it simplifies this, but the general equation of it is mass of vapor over mass of dry air, okay? And then we have relative humidity, which is mass of vapor, so it's the same thing on the numerator, but the denominator is different, okay? This is the maximum amount of moisture the air can hold at the same temperature. So that means this changes with temperature, okay? So if you're changing temperature, you're changing your relative humidity, okay? Up here, if you're changing temperature in the absolute or specific humidity, you're not changing it. Same with here, okay? There's no temperature in that relationship, so it's not a function of temperature, okay? So simplifying with the ideal gas law again, this relative humidity, you get the partial pressure of the water over that pressure, the partial pressure of the water that is max, which is basically the saturation pressure at that given temperature. Okay, so that's basically your maximum kind of partial pressure of the water vapor, and then this is the actual. Okay, so this is our actual. And these equations are just simplifying these just so you can go from one to the other. So if you know specific humidity, you can get relative, right? Or if you know relative, you can get specific. The other big thing to understand from chapter 12 was our enthalpy, right? So that's what's derived right here, okay? And that is the enthalpy of the dry air and the enthalpy of the water vapor. Even though it expresses per unit of mass of dry air, it includes both, right? So basically they took the total enthalpy of each, put the masses in, and then just divided this expression right here by the mass of dry air. So when you do that, you divide that expression by the mass of dry air, you still have the part that has water vapor in it. So here it simplifies to the enthalpy of the dry air and specific humidity and the enthalpy of the water vapor. So even though this is in units of kilojoules per kilogram of dry air, it still includes stuff with water vapor, okay? So it's just to make it easier in the conservation of energy equation, but it still has that part, okay? So that's the big thing to understand with the conservation energy equation and enthalpy, okay? And we talked about dry bulb temperature is just your typical temperature. Dew point temperature is if you're cooling the water vapor at the same partial pressure, so it's partial pressure. And when you drop its temperature in that constant pressure process, as soon as you hit the saturation temperature at that partial pressure, dew forms. So at the partial pressure of the water vapor, it's the saturation temperature. And then this is where we derive the equation for basically a wet bulb. Okay. If you have the wet bulb temperature, which is T2, if your wet bulb temperature T2, you can have an equation that gets you all the way information basically of the humidity at T1. So it's a hefty equation with lots of property lookups. So that's why the chart, the psychrometric chart, is so important, because then you don't have to do so much table lookups. Okay. So the psychrometric chart, right? We did a few examples that utilized it, and here is a nice kind of setup of showing you what all the lines are. Okay. When you look at the psychrometric chart, there's a ton of lines, but here kind of shows you the general slope and the general lines that you have there, right? Specific humidity is the horizontal line, dry bulbs, the vertical line. We see we have specific volume, we have enthalpy lines, we have wet bulb lines, right? The wet bulb and the enthalpy lines are very close in slope, as you can see there, right? And then you have relative humidity lines. Okay. And this is just showing you how to relate the wet bulb, dry bulb, and dew point. All right, different processes on the psychrometric chart, because specific humidity is on the right, horizontal lines. If you're just heating or cooling, right? If you're cooling, you're going this way, but you're not changing the water vapor amount. So you would have a specific humidity that ends up staying the same. You would see that from the conservation of mass. Or if you're just heating, you would go this way, right? Now, if you hit this curve, something else happens, which we'll get to. But all right, so heating and humidifying, because now you're changing the amount of water vapor, right? Because you're changing that specific humidity, so you're moving up, right? Same with dehumidifying, you're decreasing that specific humidity, so you'd be decreasing, your water, amount of water in the air. All right, so here is our chapter 12, chapter 14, conservation of mass and conservation of energy. Okay, so conservation of mass, we're assuming steady state, right? So it's just mass in equals mass out. And this is where we separated, we did a mass balance for dry air and a mass balance for water vapor. Okay, so simplifies to just sum of mass dry air in and out, water vapor, or water in or out. Okay. Conservation energy, again, steady state. So we just have energy in equals energy out. Okay. And you see again, if you have moist air, this enthalpy is per unit of dry air, but it includes moist air properties. So it's for moist air, and then the mass rate would be of dry air, because we've in the earlier slide again set up that enthalpy to be per kilogram of dry air. All right, so then we had examples that we went through within chapter 14 that utilize these equations. All right, so now we have chapter 15. Okay, big ones were air to fuel ratio. Okay, mass of air over mass of fuel. Okay, so we set up our chemical balance. And that would get us moles, right? So then we can use moles in the molar mass to get us the mass for air, and then do that setup and use it for the mass of fuel. The other big thing is our conservation of energy. Okay, and really all the problems in this chapter simplify to the chemical balance and the COE. You know, the solutions or in the book, they might have different versions of this, but it really, you could start off with this and simplify it to some of those other COE versions they have. Okay, they just give you a bunch of different ones, and it already cancels some terms out. All right, but the COE, right, it's for reacting flow. So we've changed a couple things. We go from mass to moles because we have a mole chemical balance. Okay, so we use moles. The other is the enthalpy is the other big one. We have the enthalpy of formation. Okay, so that's kind of in the chemical bonds there. And then we have the sensible enthalpy. Okay, and it has a subtraction of this one because the enthalpy of formation already includes everything up to 25 degrees Celsius. Okay, so that's why we got to make sure to subtract off the enthalpy at 25 degrees Celsius here when this is at whatever temperature you're at. So this is at your T-ref, and then this is again at T-ref at 25 degrees Celsius. And you get these in the back. All right, and you kind of see it here again. They show you 25 enthalpy of formation. Here's the sensible enthalpy, and you got a relative to 25. That's why you're subtracting it off, because this already includes everything up to 25. All right, so our COE, right, it has that those enthalpy terms in it, right? It's the summation, so it's here's any of the number of reactants, here's summing up all the products, right? So summing up, right, you have your moles of the reactants, moles of each of the products, and the enthalpies, which each of those components. So this dealt with a open system, right? If you were flowing, let's try to make a better arrow here. Fuel in, air, and then you have products, right? So that's fuel, air, products. So that's our combustion chamber with an open system, right? Here's closed system version, which means you have, you know, air, fuel inside. It's a closed system, right? And they react. Okay, so maybe you bring up that to a certain temperature and they react. Okay, so closed system, you know, you have del E in minus E out and the change in energy inside your system, which neglecting kinetic and potential is just the internal energy change of the products minus reactants. So we have internal energy instead of enthalpy, and really all they do is just use the enthalpy relationship. Since enthalpy is U plus PV, they just rearrange for internal energy. And you get this. Okay, so you still have those enthalpy parts, but then you have this extra little component of each of the products and reactants, which you can see here, which are negligible for solids and liquids, or RT for ideal gases, RUT. So really those two equations and your chemical balance is the main thing of chapter 15.